Let's practice factoring polynomials completely together. For number 1, we have 12y to the 4th power plus 33y to the 3rd power minus 9y squared. Remember that the first thing we're always going to want to try to do first is factor out the GCF for all three terms. So looking at 12, 33, and 9, I think 3 would be a common factor, or the GCF for the coefficients. And it looks like all three terms do have y squared as a part of them. So I'm going to factor out this 3y squared in front. If we go ahead and do that, we should be left with 4y squared plus 11y and then minus 3. At this point, this 3y squared is done because it's a monomial, but inside here we have a trinomial, so maybe we can factor this into two binomials, so we should check for that. So what I'm going to do here is I'm going to check the factors of 4, the coefficient, the leading coefficient, and I'm going to use 4 and 1, and then for the minus 3 at the end, I'm going to do 3 and 1, and I'm going to go ahead and put the negative on the 1 here. So if I go ahead and combine these, multiply 4 times 3, that'll be 12, and then 1 times negative 1, that would be negative 1. 12 minus 1 will be 11y, which is what we're looking for in the middle, right? So if we go ahead and take this 3y squared, we're going to keep that out in front, and we're going to have our two binomials that we just figured out what the factors are, right? Now on the inside here, it looks like we're going to have 4y and 1y. That's going to be the two leading terms in each of these binomials. And then the 4 was paired with a 3, so we're going to put a plus 3 on the outer here, and then we're going to go ahead and put a minus 1 on the inners here, right? So if you go ahead and FOIL this out, you can also see that this will get you the 4y squared plus 12y minus 1y, which is 11y, and then negative 1 times positive 3 is negative 3. So this would be the final factored form here. And we know we can't factor anymore because this is a monomial in front, this is a linear binomial, and this is another linear binomial, so these can't be factored anymore. For number 2, looks like we have 8x to the 5th power minus 8x to the 4th power minus 48x to the 3rd power. So looking at all of these terms, it looks like they all have 8 as a common factor, and they all have x to the 3rd power in common as well. So I'm going to go ahead and factor that out as the GCF. From the first term, we're going to be left with x squared. From the second term, we're going to be left with just an x. And in the third term, we're going to be left with a minus 6. Okay, so out in front, this 8x cubed is done. That's a monomial, but this is a trinomial. And we're going to go ahead and see if we can factor it. So the leading coefficient here is going to be a 1 inside that x squared, or in front of the x squared rather. So we know it's going to be 1 and 1 for the factors. And then for negative 6, I'm going to go ahead and use negative 3 and positive 2. Just because 3 times 2 is 6, and so this would be negative 3 and positive 2 if we went and go ahead and multiplied them together. And so I think that's going to give us what we're looking for. All right, so we have 8x to the 3rd power in front. We can go ahead and open up these binomials. All right, and then we have what? We have x and x. Those are going to be the two x terms there, and then we have a minus 3 for the outers, and then we have a plus 2 for the inners. All right, so if you go ahead and FOIL this out, you should get the same trinomial that we just started with, but this is a monomial, can't be factored anymore. This binomial and this binomial are both linear and can't be factored. All right. For number 3, looks like we have a binomial, or two terms here. We have 2a to the 5th power plus 2a to the 2nd power times b to the 3rd power. So what do they both have in common? Look for a GCF first. I think they both have 2, right? And they both have a to the 2nd power. So let's go ahead and factor that out as the GCF. And we are left with, looks like a cubed and then plus b cubed. Okay, so now in front, this 2a squared, this monomial is done. However, this a cubed plus b cubed, we want to remember, has a pattern of sum of cubes. Now, when dealing with sum of cubes, what you want to do right away from the beginning is take the cube root of each of the terms. So the cube root of a cubed, that's going to equal a. So we're going to use that in just a moment. And then if you go ahead and look at this b cubed, and you take the cube root of that right away from the beginning, and we know the cube root of it, the cube root of b cubed would just be b. It's helpful to know that because then we can use that and factor using the cube roots. Okay, so this 2a squared is going to go in front. And then what happens when we factor sum of cubes? Well, always you are going to add the sum of their cube roots. So we're going to have a plus b. Okay, so if you want to look up your sum of cubes patterns, it's always going to be the sum of their cube roots. Then after that, what are we going to do? We are going to go ahead and square the cube root of the first one, so a squared. Okay, and then what we're going to do is we're going to take away the product of their cube roots, so minus AB. Alrighty, and then finally what we're going to do is we are going to add the square of the second term, so we're going to add b squared. Alright, so sum of cubes always has the same pattern, and this would be the most factored form. So this can't be factored, this can't be factored, and this can't be factored. This is factored completely now. For number 4, let's see what we got. We have 16x to the 4th power minus 36x to the 2nd power. For 16 and negative 36, those coefficients, I believe 4 is going to be the GCF, and both terms do have x squared in common, so I'm going to factor that out as the GCF. We're going to be left with what inside here. Looks like I think we're going to have 4x squared, and then we're going to have minus 9. Okay, so this 4x squared is now done in front, but inside here what you want to recognize what pattern this is, and this is a difference of squares pattern, right? 4x squared is a perfect square and 9 is a perfect square. So this is a classic difference of squares pattern. And so what we're going to do is keep that monomial out in front here, and remember how perfect squares or difference of squares always factor out here. It's always going to be the sum of their square roots and then the difference of their square roots. So the square root of this 4x to the 2nd power, if you take the square root of 4x to the 2nd power, that's just going to equal 2x, right? And then the square root of this 9 is going to equal 3. So it's helpful to know that bit of information. So again, when you factor it, you're going to get the sum of their square roots, so 2x plus 3, and the difference of their square roots, 2x minus 3. It doesn't matter which one you write first. Okay, so this monomial can't be factored anymore. And then we have 2 linear binomials that also can't be factored, so we have factored completely now. For number 5, we have a trinomial here. We have 12x to the 4th power times y, plus 60x to the 3rd power times y to the 2nd power, plus 75x to the 2nd power times y to the 3rd power. Now I believe the GCF for all of these coefficients is just going to be 3, not a very big number. And looking at all their x's, looks like they all have at least 2, or they do have 2, and they all have 1 y in common. So I believe that's the GCF here. And if we factor that out, what are we left with? I think we have 4x to the 2nd power. I think then it's going to be plus 20xy. And then finally we're going to have plus 25, and I think it's just going to be y squared at the end. Now this 3x squared y is done in front, this monomial. However, inside here we do have a trinomial that I believe can be factored, and I think this is another special case. So notice this pattern that I'm going to show you about the special case here, right? So if we take a look at this 4x to the 2nd power, this is a perfect square trinomial, this whole thing together, and I'll show you why. So this over here, if this is a perfect square, right, if you can take the square root of 4x squared, then it's a perfect square, and that's going to be 2x. That's a square root of it. And then the last term here, the square root of this 25y squared, that's going to just be 5y. So that's a square root there. So the reason why we know this is a perfect square trinomial is because if you have squares in the front and in the back, and then if you take their square roots and multiply them together, 2x times 5y would be 10xy, and if you double that, you get this 20xy. So if that ever happens, then you know you have a perfect square trinomial on your hands, okay? So this 3x squared y is just going to hang out in front here, and try to remember how perfect square trinomials always factor. They actually always factor into 2 identical binomials, which makes them a perfect square. So this is going to be 2x plus 5y for the first binomial, and then another 2x plus 5y for the second binomial. Okay. If you want to, you can condense this a little bit as well, up to you, or what the preference is or what the directions are. But if you do this, you can also write that this is going to be the quantity of 2x plus 5y, and this whole thing is going to be squared, which makes it a perfect square trinomial. Alrighty, for number 6, looks like we have a binomial here. We have a difference. So we have 81a to the 4th power minus 256b to the 8th power. Okay, so we're trying to see if there's any GCF here, but I don't think they have anything in common. They have different variables, and 81 and 256, I can't think of anything in common. Now, if you take a look at these actually, I think that they are pretty specific numbers here. So this one over here, this 81a to the 4th power, I believe that this is a perfect square, right? So the square root of this 81a to the 4th power, that's going to be 9a squared. And if we take a look at this 256b to the 8th power, if you take the square root of 256b to the 8th power, the square root of 256 is just equal to 16, and the square root of b to the 8th power is b to the 4th power. So both of these are perfect squares, and because it's a difference, it's subtraction, it's a difference of squares. So now that we've established that this is indeed a difference of squares pattern, try to remember how difference of squares patterns always factor. It's going to be, remember, the sum of their square roots multiplied by the difference of their square roots. So we have 9a to the 2nd power plus 16b to the 4th power. And then for the other binomial here, we're going to have 9a to the 2nd power minus 16b to the 4th power. All right, again, you could put the subtraction one first if you would like to. Let's see what else can maybe be factored. This is a sum of squares, so it technically can't be factored in terms of real numbers. However, we look at the second one. Remember, this isn't linear. This might be able to be factored again, and it looks like it actually can be. This is another difference of squares. Okay, so if you take a look here, this 9a to the 2nd power, if you take the square root of 9a to the 2nd power, that's going to equal 3a. And then if you look at the 16b to the 4th power, you can actually take the square root of that again. So 16b to the 4th, square root of 16 is 4, and the square root of b to the 4th power is going to be b to the 2nd power. All right, so looks like this could be factored into difference of squares as well. So in the beginning, we're going to have this 9a to the 2nd power plus 16b to the 4th power, right? That's going to be out in front. That can't be factored anymore. However, afterwards, we can go ahead and factor the second difference of squares pattern, and looks like the square roots are going to be 3a and then plus 4b squared. And then for the next binomial, we're going to have 3a minus 4b squared. All right, so let's check to see if anything can still be factored. This is a sum of squares, can't be factored. This is just a sum of these two monomials. It's a binomial, so it can't be factored either. And this is a difference, but it's not a difference of squares, even though 4b squared is a perfect square, 3a is not. So this would be completely factored now. For number 7, we have 16x to the 4th power plus 84x to the 3rd power minus 72x squared. Now remember, first things first, we should look for a GCF. I believe 4 would be the greatest common factor for these three coefficients, and then I think x squared is what they all have in common in terms of their variables. If we factor that out, we should be left with 4x to the 2nd power plus, I think that's what, 21x, and then minus, I think, 18. All right, so this 4x squared in front can't be factored anymore, but this trinomial might be, right? So let's maybe see if we can go ahead and factor this a little bit more. So let's see, for 4 and 18, let's just start with 4 and 1. It could be 2 and 2, but let's try this one first. And then for 18, maybe I'm just gonna start with 6 and 3 and then work my way out if I need to. And let's see what's going on here. So I'm gonna think, if we go across, this would be 24 minus 3 maybe, and that would be 21. So that means that we can make this 3 negative. So this would be positive 24, take away 3. So I think that's what the pairs are going to be here. So let's take this 4x to the 2nd power, and let's go ahead and open up our two binomials. And it looks like we are pairing 4x in the first one. We'll put x in the second one, but 4x pairs with the positive 6. Let's put that on the outers with it. And let's put the minus 3 in that last location. So just checking this real quick, 4x times x is 4x squared. On the outers, we paired out, this would be 24x, take away 3x, which is the positive 21x, and then this would be negative 18 if you multiply them. So this checks out. Now this monomial can't be factored. This is a linear binomial and another linear binomial, so we are done factoring completely. For number 8, looks like we have a difference of these two terms. So we have 24a to the 4th times b to the 2nd minus 81ab to the 5th power. I'm thinking maybe this might turn into a difference of squares maybe, just because there is a subtraction, but we might need to factor a little bit, or maybe it could turn into something that has like a difference of cubes. So let's see. Let's see if we can factor out a GCF first. For 24 and 81, I'm thinking about 3 as the GCF here. So let's factor out a 3. They both have 1a, and it looks like they both have 2b. So let's factor out that as a GCF. If we do that, we should have 8a to the 3rd power with no more b's, and then minus 27. And I think we just have b cubed left inside. Okay, so just like I was maybe suspecting here, this monomial is done, but inside here we do have a difference of cubes. Okay, so we should know what the cube roots of these are. So the cube root, I'll go ahead and just write this out super clear, hopefully, of a to the third power. The cube root of this is just going to be 2a, right? That's the cube root. And then for this 27b to the third power, let's go ahead and take the cube root of 27b to the third power. I think that's just going to be 3b. All right, so those are the perfect cubes, or the cube roots of these two terms. And so let's see if we can remember our difference of cubes pattern. So out in front, we're going to have this 3ab to the second power. And then when we have difference of cubes, what we're going to always do first is we are going to take the difference of their cube roots. So the difference here would be 2a minus 3b. All right, so that's always going to be a binomial. It's going to be a difference of their cube roots. And then what we're going to do is multiply by the square of the first term. So if you square 2a, that's going to be 4a squared. Don't forget to square the coefficient and the variable. And then what we're going to do is we are going to multiply the two terms together, both cube roots. So 2a, if we multiply this 2a times 3b, that'll be 6ab. And we're going to go ahead and add that. So plus 6ab. And then finally, what we're going to do is we're going to add the square of the second term. So this 3b, if we square that, that's going to be 9b squared. So let's go ahead and write plus 9b to the second power. Okay, so we had a difference of cubes pattern here. So this monomial is done. This is a linear binomial, can't be factored. And then whenever we have the difference of cubes, this trinomial over here can't be factored either. All right, so now we're done. For number 9, we have 72x to the 6th power minus 141x to the 5th power plus 60x to the 4th power. Okay, so let's try to see if we can have a GCF first. Looking at these three terms, if you use your divisibility rules, this is definitely divisible by 3. This is also divisible by 3, and this is divisible by 3. Again, you can add their digits, and if the sum of their digits is a multiple of 3, then it's a multiple of 3. So I think we can take out a 3. Let's do that first and see if we can take out anything else, but I can't think of anything else besides that. And it looks like they all have 4 of these x's. I'm going to put 3x to the 4th power in front. Now 72 divided by 3 should be 24, and we should have 2 more x's left over here. Now for 141 divided by 3, I think that's going to be maybe 47, so I'm going to put minus 47x. And then finally 60 divided by 3 is going to be 20, so I'm going to write plus 20 here. So this monomial can't be factored, but we should try to factor this trinomial and see if we can find anything interesting. So for 24, I'm going to start with maybe 6 and 4 and see if that's going to factor. And then because this 47 is negative, but this 20 is positive, we do need 2 negative factors for 20. So maybe I'll start off with something like 5 and 4. So 5 and 4 and make them both negative here. Now if we go across, that's going to be negative 30 and negative 16. That's negative 46, which is pretty close, but not what we want. This will be negative 20 and negative 24, which is negative 44, which is also not what we want, but it is pretty close, okay? Let's try and mix things up a little bit. Instead of 6 and 4, maybe I'll try 8 and 3. And then I'll keep the negative 5, negative 4 for now and see if I need to change anything else. So this would be negative 40 and negative 12, which is negative 52. Not quite what we're looking for. This is negative 32 and negative 15 if you multiply. And negative 32 plus negative 15 is negative 47. Okay, cool. So these are going to be the outers and the inners. Okay, and let's go ahead and set up these binomials. So we have 3x to the 4th power. And let's go ahead and set up one binomial over here and then one more over here. And we have 8x and 3x. All right, that's what we just found out were the 2 factors for the leading coefficient. Now 8 paired with a negative 4, so that goes over here on the outers, and then the minus 5 goes in the last spot here. So, and just to double check this, 8x times 3x is 24x squared. Then on the outers, we do get negative 32x. On the inners, we get negative 15x. Negative 32 plus negative 15 do make negative 47. And then a negative 4 and a negative 5 multiplied do get a positive 20. So this is done being factored, this is done, and this is done. So we have factored completely. For number 10, we have this 100a to the 5th power minus 240a to the 4th power plus 144a to the 3rd power. Now looking at all three terms, I know I can divide them all by 4, but maybe there's something bigger. I'm not sure, but I'm going to start with 4, and then if I notice anything else, I will then factor again, but hopefully this takes out everything we need. And it looks like they all have 3 of these a's, so I'm going to factor out 4a cubed. And so 100 divided by 4 is 25, and then we still have 2 more a's for the first term. And then 24 divided by 4 is 6, so just put a 0 on after, so that's going to be minus 60, and I think we have 1 more a. And then 144 divided by 4, I think that's going to be, what, 36? So I think that's going to be plus 36, and then this one has no more a's. Now this 4a cubed can't be factored anymore, but this trinomial, this looks actually pretty interesting just because I think it could be a perfect square trinomial, just because the first term and the last term, both of these are perfect squares, but we can check for it, right? So if we go ahead and take a look at the first term and take the square root of this 25a squared, the square root of that is going to be 5a, okay? And the square root of 36, the square root of that is going to be 6. Now if we go ahead and multiply these two together, 5a times 6 is 30a, and if you double that, you do get this 60a, but it just means that because it's a negative 60a, you can make this a negative 6 instead, because negative 6 times negative 6 is still positive 36. So this does happen to be a perfect square trinomial, and try to think back to your patterns of what that always factors into. It should be 2 of the same identical binomials, right, if it's a perfect square. So for the first one, we'll put 5a minus 6, and for the second one, we'll also put 5a minus 6. If you're still a little bit unsure, this does make 25a squared. This makes negative 30a and another negative 30a, which doubles to make negative 60a, and then negative 6 times negative 6 is positive 36. All right, so this binomial is done, this linear binomial is done, and this linear binomial is done. And if you feel like condensing this, feel free to do so. Not really necessary, but shows that you are aware why it's a perfect square. So this will be 5a minus 6, and we can square it because it's a perfect square. For number 11, we have 128a to the 8th power b to the 3rd power minus 54a to the 2nd power b to the 12th power. So this might be a candidate for maybe difference of squares or difference of cubes, just because I see the minus, but maybe we have to factor out a GCF to see anything for real. For this one, I'm thinking I could take out 2 from both, but then I think 54, that would be 27, so I can't take out any more even numbers. I don't think any odd numbers really go into 128 I can think of off the top of my head. So let's start with 2 and then do some more stuff if we have to. So 2, and then it looks like they both have 2 of these a, so a squared, and they both have 3b, so b to the 3rd power. If we take that out, half of 128 is 64, so 64, and then we still have a to the 6th power, and then no more b's. And then minus, now half of 54 I said was 27, right? 27, no more a's, but we have b to the 9th power left. Okay, so this 2a squared b cubed was the GCF. And inside here, this is not a difference of squares because b to the 9th power is not a perfect square and 27 is not a perfect square. But I do think this could be a difference of cubes, right? So if you're not sure about your perfect cubes, remember 4 times 4 times 4 is 64. And then 6 is a multiple of 3, so that's how exponents work. It's multiples, okay? It's a little strange to think about. So if we take the cube root of this first one, it's going to be 4a squared. And if we take the cube root of this, let me go ahead and write it, the cube root of this 27b to the 9th, the cube root of 27 is 3, and the cube root of b to the 9th is b to the 3rd. So this is indeed a difference of cubes. All right, let's go ahead and keep the GCF out in front. So 2a squared b to the 3rd power out in front. And let's try to remember how difference of cubes work. So for difference of cubes, what we're always going to have first is we're going to go ahead and subtract their cube roots. So we'll take 4a to the 2nd power and then take away 3b to the 3rd power. That's the difference of their cube roots. Next, what we're going to do is we're going to take the first term and we are going to square it. So if you square 4a squared, 4 times 4 is 16. A squared times a squared is a to the 4th power. So we're going to have 16a to the 4th power. Okay, and then next after that, what we're going to do is we're going to multiply the two cube roots together, and then we're going to add that on. So we're going to multiply this 4a squared and 3b cubed. 4 times 3 is 12, and then we're just going to squish the variables together. So this is going to be plus 12a squared b cubed. And then finally at the end, we always add the square of the second one, even for sum of cubes. So if you square 3, that's 9, and if you square b cubed, that's b to the 6th. So we're going to go ahead and say that's going to be plus 9b to the 6th power. This monomial in front can't be factored. This is a difference, but not a difference of cubes or squares, so it can't be factored anymore. And this trinomial is also relatively prime. There are no common factors and nothing that can be factored out here. Finally, for number 12, we have 48x to the 6th power y minus 3x to the 2nd power y to the 9th power. Okay, so I think we have a 3. Let's take the GCF out first. So I think they all have 3. They both have x to the 2nd power, and then they both have 1y, so that's the GCF. And then I think 48 divided by 3 is 16, so we have 16, and then we still have x to the 4th power for the first term, and then minus, we took out all the x's. I think we still have 8 y's for the second one, so y to the 8th power. Okay, so this monomial in front is done. Now inside here, notice this is a difference of squares. So the square root of this 16x to the 4th power, the square root of that, square root of 16 is 4, and the square root of x to the 4th power is x to the 2nd power. And then for this y to the 8th power, if you take the square root of that, remember anything to an even power is a perfect square. The square root of y to the 8th is y to the 4th, right? Just divide by 2 when you're taking the square root of exponents. So this is a difference of squares. So in the beginning, we have this monomial of 3x squared y. And try to think about how difference of squares patterns factor. So we should have a sum of their square roots and a difference of their square roots. So 4x to the 2nd power plus y to the 4th power, that's a sum of their square roots. And the difference would be 4x to the 2nd power minus y to the 4th power. Alrighty, so this is done being factored, and this is also done. This is a sum of squares actually, but there is no sum of squares pattern. If you look over here, this is actually another difference of squares. So you gotta factor again, so be careful and look for these things, okay? I'm gonna go ahead and write this underneath because I have some space. So the square root of this 4x to the 2nd power, that's going to be 2x. And if you look at this, y to the 4th power, that's another perfect square. So we have y to the 4th power, but the square root of that is going to be y to the 2nd power. So this one's going to factor again, right? So let's take this 3x to the 2nd power y right in the beginning. And then the second one can't be factored anymore, this binomial of 4x to the 2nd power plus y to the 4th power. We go ahead and close that off. That's a binomial. And then if we're going to go ahead and factor this into a difference of squares one more time, then the square roots, we're going to have the sum of them, so maybe 2x plus y squared multiplied by the difference of them, 2x minus y squared. All right, so this is done, this is done, this is done, and we can't do this again just because y squared is a perfect square, but 2x is not. Okay, so this is factored completely now. So there you have 12 different practice problems on factoring polynomials completely. Some of the things you want to remember are factoring trinomials. You also want to try to remember your difference of squares pattern, as well as your perfect square trinomials pattern. And finally, the last two we used were the sum of cubes and difference of cubes. And maybe a good thing to remember is just in the beginning, always try to factor out GCFs first before you do anything else. Usually it makes the other patterns a little bit more obvious afterwards. So that just about wraps up this video. If you found it helpful, please consider giving it a thumbs up. As always, keep up the great work, and I'll see you in the next one.